I need to talk a little bit about climate change and climate change in relationship to chemistry. We'll look at climate change generally first of all, and then talk about climate change. So, we first of all need to talk about something called radiative forcing. And this is the change in the net radiation balance of the tropopause. The tropopause is the dividing surface between the stratosphere and the troposphere, and that's where the temperatures are minimum, and where gas absorption by a gas such as CO2 is most effective, because its temperature is at its lowest at that point. So this is the net radiation balance of the tropopause caused by a particular external factor in the absence of any climate feedbacks. It's just a formal definition. These forcing mechanisms can be caused by changes in the atmospheric constituents, such as the increase in greenhouse gases, aerosols due to anthropogenic activity, and changes in other components of the Earth-atmosphere system, such as changes in the surface albedo, which is a fraction of incoming radiation that's reflected. Albedo changes are caused, for example, by changes in vegetation, which is burn scars. Albedo is also changed by the deposition of soot on snow. So if you take the Arctic and if you take the Arctic and soot is deposited on the snow, then the albedo is reduced, reflectivity is reduced. So these are mechanisms of radiative forcing. Absorption of long-wave radiation from the surface and emission of long-wave radiation at lower temperatures is the energy gained by the Earth-atmosphere system. The surface is emitting infrared radiation, and it's being absorbed by gases, and that absorption and re-emission process is most effective in retaining energy in the Earth's atmosphere up at the lower temperatures up here. There is also reflection of solar radiation back out to space. So clouds reflect, white clouds reflect radiation, and so cloud cover is a cooling process. So those are reflective aerosols, and then these are absorbing aerosols, what's called the direct effect of absorbing aerosols. So if you have aerosols which consist of black carbon, then they will absorb radiation, and that will increase the temperature of the Earth's surface. So aerosols are complicated. This is a diagram which comes from the IPCC 4th assessment report. The IPCC is the Intergovernmental Panel on Climate Change. And this report was from 2007. The next report will be later this year and into next year. And these are very detailed analyses by hundreds of, in fact, thousands of scientists, economists, and social scientists, and excuse me, looking at the physical basis of climate change, the impacts of climate change, and mitigation measures, and then general policy overviews. They are conducted by a scientific panel, as I said, consisting of hundreds of people. And then governments are involved in the final phraseology that's used in the reports that are produced. And these assessments are based on peer-reviewed publications, entirely based on peer-reviewed publications. And in the physical science basis, much of it is done on the basis of
global climate models, which are carried out in many places, different models in different places, Europe, China, the US, etc. And comparisons between these models and the predictions of climate change on these models. And I would strongly encourage you to follow this fifth assessment report as it comes out. There are going to be significant changes from last time, but I think the overall message is likely to be the same. And the message is very measured. So, for example, the fourth assessment report, a statement was that it is very likely that climate change is being caused by anthropogenic emissions. And by very likely, they mean more than 90% probability. So the language is very measured and also reasonably quantitative. And it's a good place to go to get a reasonably, well, not just reasonably, a very detailed view, overview of what's going on, and an assessment made by the vast majority of climate scientists. I mean, some people don't agree. There are climate skeptics, but by and large, I think it's fair to say that they are in the minority. And this is an overview which comes from the majority of these climate scientists. So these are radiative forcing values. It's in watts per square meter. So these are the changes in the energy at the Earth's surface due to these overall changes. Oops. And CO2 is the major contributor, but you can see that there are these other gases, methane, N2O, halocarbons, which contribute something like half of the value of CO2. And then ozone. Stratospheric ozone leads to cooling. Tropospheric ozone leads to warming. So ozone is a greenhouse gas, a secondary greenhouse gas. It contributes. And all of these gases contribute because of their infrared absorption properties. So they absorb infrared radiation scattered from the Earth's surface, emitted from the Earth's surface, primarily emitted from the Earth's surface. This infrared radiation, with the Earth acting, if you like, as a black body and emitting infrared radiation. And this infrared radiation can be absorbed by these various gases. And so these are the changes that have taken place really since 1750, since the Industrial Revolution. Then these are changes in surface albedo, changes in land use. These changes are primarily due, for example, to changes in agricultural practices, which make the Earth's surface more reflective. And this warming effect is black carbon on snow. And then aerosol. So aerosol is primarily cooling, but these error bars are absolutely massive. So these are the error bars on the CO2, these other greenhouse gases, and on ozone. So the confidence in predictions of these are high, or the assessment of radiative forcing for these is high. For ozone, it's medium. For aerosols, it's low. So our understanding of the atmospheric loading of aerosols is low, but also our understanding of exactly how they interact with the climate system is low. Yeah?
How would you even know what the cloud albedo effect would be in 1750 to compare it to? What kind of data is available on that?
You've got to remember that what we're talking about here is the impact of anthropogenic processes on climate. And those can be, you can calculate those. So what the way in which they've done that is they've calculated the impact of anthropogenic processes on aerosols and hence on cloud. So, for example, if you look on a nice sunny day in a region where there is considerable aircraft activity, then you can see the clouds. The clouds are forming from the contrails, and the contrails are having a substantial effect, a cooling effect, as it turns out, because of the production of clouds. And so you can estimate these things. You can calculate. Okay, and so that's the total net anthropogenic effect. This shows concentrations of CO2 and methane at various locations. There are some variations from one location to another because of local production of CO2. There are annual variations associated with emissions, amongst other things, emissions of VOCs. Other greenhouse gases, just very briefly, N2O, CFCs, their concentrations are decreasing substantially, but nevertheless they do have a very considerable effect on radiative forcing. And ozone, approximate doubling of concentrations between pre-industrial and the present day. Central to all of these calculations are global models. And so this shows you the sort of global models that are used. And so they're very much like the models that you would use in combustion, in that they are gridded. They're what are called Eulerian models. So you have grids typically of the order of 30 kilometers, so they're quite coarse grids, 19 levels in the atmosphere, 20 levels in the oceans, and 5-kilometer grid squares there. And you just cover the globe with these grids. And then this shows the evolution of models in the 1970s, just looking at the atmosphere and then incorporating the land surface. Very important interactions between the atmosphere and the land surface, not least because of the emission of biogenic species. And then the ocean and sea ice, incorporating sulfate aerosol, non-sulfate aerosol, the carbon cycle. So this is the cycle in which carbon is fixed in the oceans and emitted into the atmosphere. And then coming along down here, atmospheric chemistry. The atmospheric chemistry is extremely limited. It's very, very heavily parameterized because, I mean, those of you doing CFD will know that you can't put too many reactions in. And in big global models like these, big global climate models like these, you can put relatively little chemistry in. But it's heavily parameterized. So what they do is they try and incorporate the bulk of the important processes that are there. So here's the carbon cycle, vegetation, emissions from industry, etc., exchange with the oceans, and then exchange between the surface and the deep water. And these are the timescales of these processes. So this exchange here is very, very slow indeed, and these exchanges are very fast. And then these are processes in atmospheric chemistry models. So you've got transport, deposition, emissions, and so on. Yeah? Sorry? In a very, very limited way, because that's one of the things that, I mean, a lot of the oceanic chemistry, I mean, is incorporated, for example, in terms of emissions. So you get emissions from the ocean. You get also deposition in the oceans. So it's incorporated in that sort of way. And then you've got the processes which lead to taking of the CO2 down. But the sort of basic CO2 aqueous chemistry is certainly incorporated in mean more in a timescale way than anything else. So the detailed reactions aren't included, but the timescales are included. So I mentioned these various emissions scenarios, and these show the temperature increases predicted over the next century, depending upon the scenarios which are used. And generally speaking, the thoughts are of the order of 2 to 4 degrees centigrade rise by 2100. What's the impact on atmospheric chemistry? So this is surface ozone throughout the globe in the 1990s. So you can see high concentrations in some regions. We talked about southeast US over here, so relatively high concentrations there, and also in these tropical regions around here. So this is the change in surface ozone if over the next between 1990 and 2020. So we're almost there. If there were no climate change, if there were no changes in temperature, and big changes over India for some reason, which I think were discussed in this paper, but I don't remember what they were. And these interesting little blobs here, which are due to shipping. One of the things about shipping is that the worst possible fuels seem to finish up in ships. So that the controls over fuels used in ships are not very high. They're getting better. But shipping is a significant source of emissions, especially, I mean, if you look in this region here, this isn't shown in ozone, but in terms of NOx emissions, in this region around here, the shipping is massive, and the NOx emissions are substantial from shipping. And these little blobs here come from shipping. So this isn't a definitive work by any means, but it gives you some idea of the changes that are predicted to happen, negative in the southern hemisphere, positive in the northern hemisphere, in the absence of climate change. And these are changes in temperature over this same sort of period, 1990 to 2020. These are again model predicted and by no means validated in any way. And this is the change in ozone. And it's interesting to look at why ozone should change because of changes in temperature. So first of all, warmer temperatures lead to higher humidities. Higher humidities, especially over the oceans, simply because the temperature's gone up, the air is more able to carry more water vapor. And the net result of that increase in water is that you're going to channel more of the ozonotic D in the direction of OH formation rather than the direction of ozone regeneration. And so this is going to give rise to an increase in OH. There are also increases in isoprene emissions. Isoprene is emitted by vegetation, as we've said, and the emission rate increases as the temperature goes up. So as the temperature goes up, there are increases in isoprene emission. And that has two effects. One of them is to increase ozone formation, but also to reduce OH there. Yeah, I think actually I'll skip this. Whoops. Remember, this is a reminder about PAN, and PAN is a reservoir species and allows NOx to be transported. And it's a major player in continental transport of pollutants. And the changes in temperature are going to reduce the amount of this transport because PAN is going to dissociate more rapidly. this gives you an idea of what's meant by albedo and how complicated it is as a problem. So this shows you, these are fires, forest fires in Portugal, generating aerosol, and that aerosol being advected. And you can see that over the land, the aerosol from the fires is more reflective than the land, and so this is smoke from the fires giving rise to an increase in the albedo in this region here. But over cloud, so this, what happens is the smoke from the forest fires rises very rapidly and then moves at quite a reasonably high altitude and often above the clouds. And you can see in this region here, it's reducing the albedo because the clouds, it's less reflective than is the clouds. So this is decreasing reflection over cloud and an increase in reflection over the ocean. So it's a fairly complicated process. And remember, these global models are really quite coarse, and some aspects like this can't really be properly incorporated in the models. Okay, that's a brief discussion of climate change generally. Now let's have a look at chemical mechanisms. So this is a brief description of the chemical mechanism for oxidation of a volatile organic compound. The VOC can be photolyzed if it's a carbonyl, react with OH, react with NO3, react with ozone, produce these species down here, which react, form oxygenated products, which can then go back and be oxidized again. So if we step through this, here's a route through for this VOC, reacting first of all with OH, then forming a peroxy radical, then an oxy radical, and then an oxygenated product. And then that oxygenated product goes round in this cycle. And so this is what I mean when I said earlier on about generations within chemical reactions. So the first generation was that first pass through to this oxygenated product. Each of these steps, excuse me, each of these steps is very fast. It involves, they involve radicals. But then this oxygenated product is a stable molecule, and so it reacts more slowly, and then it reacts in one of these various ways and comes round again, produces another oxygenated product, and that goes round again. And so we have a series of generations of reaction. This is, I mentioned yesterday, this huge chemical mechanism, and this is the website for it. It's called the Master Chemical Mechanism, and it's a detailed analysis of the oxidation of about 140 different organic compounds. That's why it's so big, because it involves the oxidation of so many different compounds. The oxidation of each of them is somewhat simpler than the combustion of each of these compounds. The numbers of reactions involved is significantly less. But on the other hand, we have in the atmosphere to worry about many more compounds being present. So this is the first page of the isoprene mechanism. So if you search for isoprene, then you get this mechanism here. So reactions with NO3, with ozone, and further down with OH, forming these species here. What you can do is you can take this mechanism, you can mark isoprene here, and you can extract the chemical mechanism. So here's the chemical mechanism for isoprene oxidation, which goes on for a long way down here. It includes the reactions and also the rate coefficient. Some of these rate coefficients for the simpler compounds have been measured directly. So for example, OH plus C5H8, these have been measured. This is the overall rate coefficient for reaction of isoprene with OH. And an important thing is here is the fraction of reaction occurring in by addition at different locations, which lead to different peroxy radicals. And those have been inferred by other experiments which are looking at products of the reaction. Now, just as with combustion, what we need to be able to do is to evaluate these mechanisms. There are many rate parameters that have been estimated, and so we need to check the mechanisms and their performance against measurements of whole systems. And this is done using atmospheric chambers. So this is a large chamber in Valencia in Spain. There are 2 chambers which can be closed, and they're heavily instrumented. So here's the instrumentation in this particular chamber. There's UV absorption, determining concentrations of a variety of species using UV spectroscopy, infrared spectroscopy, gas chromatography, mass spectrometry, and also measurement of radicals. So you can measure radical concentrations measure OH, for example, and HO2 using laser-induced fluorescence. This is a similar chamber in Jülich in Germany, and this is even more heavily instrumented. And one of the nice things about it is that people can bring their instruments in shipping containers like these. So if you do field measurements, then you use shipping containers to put your instruments in, but you can bring them to this chamber and do intercomparisons of the various techniques that are used. So a variety of techniques might be used for looking at OH, and you can intercompare these techniques and see if they agree. This is an indoor chamber. This is the one we have in Leeds. There's no sun in Leeds, so you have to do the experiments inside. So this is called HIRAC. And so these are the lamps which are used to generate the species. And infrared spectroscopy is used extensively. You can cool. It stays down to 230, but it's very difficult to get below about 260 K. GCs over here. And we can measure OH and HO2 using a technique called phage, which relies on laser-induced fluorescence, and also cavity ring-down spectroscopy to look at NO3. So it's heavily instrumented again, but it's not using sunlight. It's using light which covers much of the ultraviolet that's important, but clearly has a different spectrum from the sun.
Professor?
Yep.
What are the scaling parameters you have to match when you're doing like a chamber versus like an atmospheric measurement?
One of the things that we try to concentrate on is hydroxyl radical chemistry, and because it's driving so much of it. And in the atmosphere, the lifetime of OH is about a second, so it doesn't move very far. And so transport is not an important process. So what you have to try and do is to measure the concentration of absolutely everything else in that region of space around where you're making the OH measurements. So that's the way in which we look in detail at chemical mechanisms in the atmosphere, by focusing on the radicals that are driving it and the short-lived radicals that are driving it. You could also do similar experiments with NO3. Slightly less easily because it has a longer lifetime, but nevertheless you can do similar experiments with NO3. In the chamber, what you're doing is you're working. You want to have that chamber well mixed, so that the chemistry isn't changing significantly over the chamber. And the major problem with chambers is reactions occurring on the walls. And so there are reactions occurring on the walls that that generate radicals and that consume radicals, and you have to characterize those. And so that's, but overall, what we're trying to do is to compare chemical mechanisms with what's going on either in the atmosphere or in the chamber, and we try to make sure that transport is not a significant component of it. So that the scaling issue is not really there. This is an analysis of ethene oxidation in the chamber in Valencia, and these are the measurements here and the model, and the uncertainties in the measurements and the uncertainties in the model. So these are global estimates using Monte Carlo methods in how the model is performed, in the uncertainty in the model. And this is, these were calculations done while she was at Leeds by Judith Zador, which the chemists amongst you, combustion chemists amongst you may know. Judith is now in Sandia. These are looking at other species, ozone. So that was ethylene. This is looking at ozone. And this is showing that there, even for ethylene, there are significant, just about significant differences between the model and the measurement. You can perform sensitivity analyses in the same way as you can with combustion mechanisms. And these are under low NOx and high NOx conditions. And one of the key reactions here is this reaction OH plus NO2 going to nitric acid. This is now better characterized than was the case when these calculations were done, but it's proved to be an interestingly complex problem to solve, the reaction between OH and NO2. Under low NOx conditions, it's this reaction here between the peroxy radical formed from OH addition to ethylene and NO, and there's only been a single measurement of that rather important rate constant, and that's something that really ought to be addressed. These are aromatics, and aromatic chemistry is horrifically complicated in the atmosphere. So this is toluene, and the main routes are addition of OH to the ring, forming phenols, and these then react with NO3, and this leads to the formation of aerosols. The other important reaction is this one here, which we understand very poorly, and it involves ring opening and forming these dicarbonyls down here, glyoxal, methyl glyoxal, and these C4 and C5 dicarbonyls. So that's the mechanism that's contained inside this master chemical mechanism. How well does it perform? Well, not very well at all. This is the toluene decay, the experimental toluene decay. This is what the model predicts. And toluene in the chamber is only removed by reaction with OH. So what this is saying is that our mechanism is underestimating the OH concentration by about 50%, by a huge amount. And so there is some route to forming OH that we really don't understand in these aromatic systems. There are also problems with the way in which we simulate NO2. We're significantly overestimating the amount of ozone that's there. And all in all, there are some real problems with our understanding of aromatic chemistry. Those slides were taken from a campaign conducted in Valencia, in Spain, in about 2000, between 2000 and 2003, 10 years ago. But our understanding has not improved significantly since those experiments were done. This is the oxidation of alpha-pinene. Alpha-pinene is a biogenic compound, C10 compound. It's again emitted from vegetation, mainly coniferous forests, and that's in much better shape. So here's the alpha-pinene decaying away. This is the NO2. We're not simulating that too well. and here is NO. So alpha-pinene is somewhat better understood than the aromatics. But how well do we understand organic chemistry generally? This is an interesting salutary tale related to what we were talking about yesterday. The need to understand the fundamentals of chemical mechanisms, not to simplify things too much before you genuinely understand them. And this relates to missing radical sources. I referred to some missing radical sources in aromatic chemistry that we don't yet understand. And these are missing radical sources mainly with biogenics that, again, we don't really understand. So these were experiments which were conducted by a German group from the Max Planck Institute in Mainz. And what this is doing is looking at the hydroxyl radical concentration and comparing the observed radical concentration with the modeled. And you can see that the modeled concentration significantly underestimates the observed concentration. This is fudging the mechanism so that you get good agreement between the two. And they found that they had to put in extra OH sources, substantial extra OH sources, in order to explain what was going on. And they said that to explain the observed isoprene concentrations, the effective rate constant for reaction of isoprene with OH would need to be reduced by about 50% compared with the lower bound of the range recommended by IUPAC. IUPAC is an evaluation panel. So what that means is that the rate constant is something like a factor of 2. They need a rate constant which is something like a factor of 2 less. And this is one of the best studied reactions in atmospheric chemistry. So it's very unlikely that it's out by as much as that. And a reasonable explanation for this lower effective rate constant could be a segregation of isoprene and OH in the mixed layer. So what they're saying now is that possibly there may be some sort of segregation of air above forests, which leads to a separation between OH and isoprene. And I'm not, I'm skeptical, but I'm not a good enough fluid dynamicist to comment on that. So what you can do is measure the lifetime of OH. This is an instrument in Leeds. It's actually an old instrument in Leeds. But what you do is you sample air from the atmosphere and then generate OH and then measure the concentration of OH as a function of time following the OH injection. And so you can measure the lifetime of OH. So the lifetime of OH is equal to 1 over the sum of Ki xi, where these are all the species that react with OH. In addition, from this you can get the rate of removal of OH from the atmosphere is going to be equal to the concentration of OH divided by its lifetime. Okay, think about that, and I'm sure you come to the conclusion that that's correct. So this is the way in which the experiment occurs. So ambient OH is removed in the sample line. You inject OH, and then this is a flow tube that measures its concentration. And the concentration is a function of time. You basically move this injector up and down, so you change the time between OH injection and the point where you're monitoring its concentration using laser-induced fluorescence. And so these are the sorts of plots that you get. So this is the physical loss when there's nothing present. These are field measurements where you've got VOCs present, lots of Xi's present, and so you can measure the lifetime. And you can combine the measurement of OH reactivity with measurements of OH, HO2, and concentrations of OH sources, such as ozone, nitrous acid, etc., to check the budget balance, to check what's going on. And these are measurements made by the German group from Jülich in the Pearl River Delta region of China. And so here are the measurements of OH and HO2. So these give you the absolute concentrations of these species. And here are the lifetime measurements down here. And this is the OH reactivity. So this is taking the reciprocal of this lifetime and calling that the reactivity. So the reciprocal of this would be the lifetime. So you can see that the lifetime decreases during the afternoon and is somewhat, the lifetime increases during the afternoon, the reactivity decreases and is higher in the morning. And what is clear is that isoprene and its oxidation products are important in removing OH during the afternoon. Okay, now this is analyzing the data. So this is the rate of OH loss, which is calculated in this way. OH divided by the lifetime, or OH multiplied by the reactivity. You've measured the OH concentration, and you've measured its lifetime. So you can calculate the OH loss rate directly. You can also calculate, you've measured HO2, so you can calculate the rate at which HO2 reacts with NO to regenerate OH. And in the morning, that's important. But in the afternoon, in this location, it turns out that NOx is removed quite rapidly. And so the NOx concentration falls, and so the rate of this HO2 plus NO reaction falls. And then this is the rate of formation from the various sources, which is quite small. And you can see that there's a very substantial imbalance here. So the total rate of production of OH, which is this plus this, is very much less than the total rate of loss. And there's no model involved here at all. These are all direct measurements. So there's something strange going on here that we don't understand. There is some source of OH other than what we've got here from production from these various sources and the feedback from HO2 to NO. And I won't go through this in detail, but this is a suggestion that was made by Jeff Peters from Leuven in Belgium. And this is exactly the same sort of chemistry that you get in autoignition. So what he's suggesting is that this peroxy radical, so OH adds to isoprene, and then that adds an O2 there, and then you get a transfer of a hydrogen atom from here to there. So you form this hydroperoxy radical, from here to there, this hydroperoxy radical, which then reacts with O2, abstracting this H here and forming this carbonyl compound. And this carbonyl compound photolyzes in the atmosphere very rapidly and generates OH. So what Jeff is suggesting here is that this is an important route to OH formation using chemistry which hadn't really been considered previously in the atmosphere, because it was thought that these sorts of processes would be too slow. But isoprene is really quite different because of the presence of this double bond which delocalizes and stabilizes the species that are involved in this transfer here. And he suggested that this rate constant was of the order of 1 second to the minus 1. And so what this is doing, so here's a cycle here, OH, RO2, RO, HO2. And what he's suggesting is that this RO2 species here doesn't have to go all the way through to HO2 before it regenerates OH, but it can do so via this cycle here. So this is an interesting proposal, and it isn't yet clear. Some people have done calculations of what the impact would be in the atmosphere, and it's clear that it would have a very significant impact. But it's not clear that it's correct. It's a calculation. These systems are difficult to do calculations on, and it may well be that that the process, experiments done in California suggest that the reaction does occur, but it occurs more slowly than Peters was suggesting from these calculations. So this is a very active area of research in atmospheric chemistry. These sorts of reactions do occur. So here's the reaction between OH and acetylene, which it gives very rapidly gives formation of OH. So what's happening is that OH adds to acetylene, and then what happens is that reacts with O2 and forms these compounds down here, which dissociate over these very low barriers and generate OH plus glyoxal or HCO plus formic acid. And so this is an example of a system, a very strange system because of the presence of the triple bond, which stabilizes these transition states, brings these transition states way, way down, and allows this OH regeneration. And this species here, this intermediate, is that this is the peroxy radical, and this is the hydroperoxy radical that we talked about in the last slide, but for this particular system. So this is OH plus C2H2 plus O2. So this does occur, and one of the interesting things about it is that, so this is a science paper on the system. This demonstrates from both experiments and theory that this reaction is occurring before the adduct between OH and acetylene before it's been fully thermalized. And so we're getting reactions of vibrationally excited species, which changes the ratio of the concentrations of the products, HCO and OH. So just a final slide on the future. Energy-related CO2. This is really a comment for you as combustion scientists. Energy-related CO2 emissions increased by 20%, consistent with a long-term rise in the average global temperature in excess of 3.5 degrees. So that's by 2035. That's a suggestion by 2035. Whether that will happen or not is debatable. 90% of the projected growth from non-OECD economies, 90% of the projected growth is occurring from non-OECD economies, with 30% of it occurring in China. So it's the growing economies which are contributing primarily to this increase in CO2. These are actually CO2 equivalents. So they include methane, N2O, etc. The share of fossil fuels in the global primary energy consumption is likely to fall slightly by 2035 from 81% to 75%. So by 2035, fossil fuels are still playing a major role in the global primary energy consumption. On planned policies, rising fossil fuel energy use will lead to irreversible and potentially catastrophic climate change unless we do something about it. And that's something I'm sure is going to come from a variety of approaches. Improved efficiency of combustion, improved insulation in houses which are heated, carbon capture and storage as a way of removing CO2 from combustion sources, other power sources such as wind, solar, etc., etc. So there is no, I'm sure there is no silver bullet that is going to sort this lot out. It's going to come from a variety of sources. And much of it necessarily is going to come from improvements in the way in which we burn fuels and generate energy from the burning of fuels. So that's basically you guys. So it's improvements that are produced from this community which are going to help to avert this irreversible and potentially catastrophic climate change. There are many people from China here, and China is responsible for nearly half of the global coal use in 2009 and holds the key to the future of the coal market. It's got an ambitious 12th five-year plan for 2011 to 2015 to reduce energy and carbon intensity through enhanced energy efficiency and diversifying the energy mix. So China is going to play a major role in these processes here. So these are thoughts for you as combustion scientists and the way in which you're going to contribute to these changes. Okay, this is not again, this is a new slide. Excuse me. So this is just a list of books and reading. So if my discussion of kinetics has been less than lucid, then I can point you to an excellent book which will help you understand it hopefully a little bit better. So it's quite old. It was published in 1995, but kinetics hasn't really changed over that period of time. Radical kinetics, this again is something from me. So this is a feature article in JPhys Chem. So this is really me looking back over 30 years of radical kinetics. Sorry, I don't have the page number. I just have the reference. It's recently come out. If you want to know more about master equations, then these are two key references, one by John Barker and one by Stephen Klippenstein and Jim Miller. John Barker uses a different approach to solving master equations. He uses a Monte Carlo approach, and he has a code available called Multiwell, which a lot of people use. And so it's worth having a look at that paper and also having a look at John's website. He's at the University of Michigan. Autoignition chemistry. This is a really beautiful article from Sandia in Progress in Energy and Combustion Science, which takes a general look at autoignition chemistry, but also the ways in which recent experiments and recent theory have changed the way in which we should be thinking about autoignition chemistry. If you're interested in atmospheric chemistry, there's this nice book by Richard Wayne called Chemistry of Atmospheres, published by Oxford University Press, and it's very detailed. There's a lot of stuff in there that's very valuable. But also, I would strongly recommend that you have a look at this IPCC fourth assessment report from 2007, and the fifth assessment report, which will come out next year. I think, actually, the first report on the physical science basis will actually come out in September of this year. So I'd strongly recommend you have a look at that. I showed you right at the beginning the town where I live called Ilkley, and this is Ilkley Moor. A moor is a region which doesn't have very many trees on it at all, but has heather and peat, and it's a very, very interesting and beautiful sort of area. And this is a song which I won't sing, And believe it or not, this is English. It may not look like English, but this is in some ways is the anthem of Yorkshire, which is the county which Ilkley is in. And it says, "Where hast thou been since I saw thee, I saw thee." And translating that, it means, "Where have you been since I last saw you?" And then, "On Ilkley Moor bart at," and that means, "On Ilkley Moor without a hat." "Where hast thou been since I saw thee?" You can translate it yourself. "Where hast thou been since I saw thee? On Ilkley Moor bart at, on Ilkley Moor bart at, on Ilkley Moor bart at." And this song goes on and on and on and on. And basically, because this guy was on Ilkley Moor up here because he was courting Mary Jane. Do you know the word courting? He was having a relationship with this lady, Mary Jane. And they suggested that because he was doing this without a hat, in this is not a very dry area, there's a lot of rain, that he was going to catch his death of cold. And then, having caught his death of cold, we'd have to bury him. And when he was buried, the worms would come and eat him up. So then worms will come and eat the up. And then ducks will come and eat up worms. And then we will eat up ducks. So the worms eat him up, the ducks eat the worms, we eat the ducks, and then we will all have eaten thee. So this is the anthem of Yorkshire, and this is Yorkshire dialect. And I just thought it would be nice to leave you with those thoughts. Okay, thanks very much.
Today in the evening, we have another chance to thank Professor Pitt. It's I've watched him giving the lectures. It's so dynamic. It's impressive. Again, thank you.